Thank you everyone for coming. Let's talk about containers and the lies that they are. My name is Larry Garfield. You may know me online as Krell. If you want to make fun of me on Twitter during the talk, that's where you do so. I generally encourage it. I'm the Director of Developer Experience at Platform.sh. We're a continuous deployments cloud hosting company. A bit more on us later. I'm also a member of the PHP Fig core committee. For the non-PHP people in the audience, that's the PHP standards body, or more kind of like the United Nations of PHP with all the good and bad implications that has. And I'm also now the author of Thinking Functionally in PHP, available now from LeanPub. Stick around to the end of the talk, we're giving away a copy. If you don't win, go ahead and buy a copy of the book. It's a good introduction to functional programming, category theory, and so on, but done all in PHP. So it's nice and approachable to people who don't know Haskell. All right, let's talk about clouds. Wrong clouds. I mean cloud-based hosting, because people keep saying that cloud-based hosting is the next big thing. That's cloud this, cloud that. What does that actually mean? Clouds, okay, cloud is a particular type of hosting environment, a computing environment. And usually people say that they're built using containers. Okay, what's a container? Probably not that. That's not the kind of container we mean. That's my lunch. I'm pretty sure we don't host websites on my lunch, at least I hope not. I also sometimes hear people talk about containers and compare them to shipping containers. And I'm pretty sure that's not a server farm, so not quite that either. The ping time to those boats would be terrible, so you don't want to put your websites there. Some of the marketing around containers talks about whales. I see that picture a lot, but no, that's not a container either, except maybe for plankton, I don't know. So that's not a container. When people talk about containers, often they talk about Docker. Okay, Docker is a particular program that uses containers, but that is not what containers fundamentally are. Docker is a particular type of container. So that doesn't help us. So what are containers? Fundamentally, containers are lies. That's it. Everything you've heard about containers is a lie, including the containers themselves. That's the point. All modern software is in fact built on a deep pile of lies, and that is what makes it powerful. And containers are simply one more layer of useful lie on top of everything else we do as developers to lie to our computers. So to understand what containers actually are, we need to back up and look first at the first lie, the primary lie that underlies all modern computing, and that is the process. This is a processor, a CPU. In particular, this is a very old CPU, Intel Pentium. Those of you old enough to recognize this picture know this is the type of Pentium that can do floating point math. If you don't know that joke, then you're too young. Any CPU is fundamentally a single-threaded device. It has a linear series of instructions, and it executes them one at a time in order. There's also a specific place in memory, a specific register called a program counter. The program counter is the address of the next instruction to execute. So normally it will just execute one instruction and then the next and then the next and the next. But one of the things an instruction can do is conditionally set that program counter to point to somewhere else, allowing the program to branch and make decisions. And that's how virtually all modern hardware works. And it's actually really, really fast, especially modern hardware, but it has to do these really slow things like talk to memory or talk to a hard disk, or God forbid, talk to something on the network and do I/O, which takes several orders of magnitude more time than executing an instruction. So the CPU is just sitting there waiting. It'd be really nice if we could spend less time waiting and the CPU could do something else in the meantime while it's waiting for a message to come back from that horribly slow hard drive that you have. To deal with that, we introduce an operating system. This applies to pretty much any operating system on the market. An operating system is software that manages software. It has a special relationship with the CPU, and there are things that it gets to do that other programs don't. There's a lot of pieces to it. Operating systems are big and complex. One part of it in particular that we're concerned about is called the scheduler. The scheduler coordinates with the CPU, and periodically the CPU will tick, and every tick will trigger a timer interrupt, which means stop what you're doing and set the program counter to this specific known place in memory to point to a specific instruction that's part of the operating system called an interrupt handler. And the interrupt handler goes, oh, I've been pinged. Okay, start using that series of instructions now over there. That's called a context switch. And thousands of times a second, the CPU will tick, the timer interrupt fires, the operating system says, oh, that one. And we'll switch the program counter out to point to a different series of instructions. And this allows the operating system and CPU to collaborate and lie to you that the computer is doing multiple things at once, when it's actually just switching between them faster than you can notice. These days, of course, we have CPUs with multiple cores, and we have programs with multiple threads. All that really means is multiple program counters. With multiple cores, that same thing is happening, just with a different program counter in each and its own set of instructions. Multiple threads are multiple program counters on a single series of instructions, but it's fundamentally that same basic process in any case. Okay, but then how do you keep track of all of those programs, those processes, and which program counter is which, and the memory used by each one? Collectively, each of these streams gets called a process. A process is the name given to a stream of code, a program counter, a process ID, that's just a numeric ID so that the operating system can keep track of them, and some block of memory that's a scratch space for the program to use for whatever data it's manipulating. This is, again, virtually every operating system today. Processes then can talk to the operating system by passing messages to it and ask about the system, ask about other processes, ask about the hardware. And they can ask what other processes are running, what are their IDs, can I talk to them? Oh, I can talk to that one, all right, I'll send a message from one process to another via various mechanisms. They can ask the operating system things like, what kind of hardware do I have? What's the host name? How many hard disks are there? What's the file system, and so forth. Processes can also spawn new processes, either by forking, which means you take one process, clone its memory, and give the new one a second, its own program counter with a new process ID, and now you have two processes running. Or by pointing at a file on disk and saying, hey, operating system, load that and start a program counter on it. And that starts up a new process. When you create new processes this way, you end up with a hierarchy of this process spawned this process, spawned this process. The first process that starts gets called init and is responsible for coordinating and controlling all of the other processes. Implementation details vary a bit. Even just on Unix systems, there's a number of init systems available. There's the classic init.d. There's systemd, which is a newer one that most people are using now. At Platform, we use one called runit. There's various other options, but that's the basic idea of a hierarchy of processes that spawn processes. We also, though, have to think about memory, not just the instruction set. Typically, in your actual physical hardware, the code and data are spread out at random across your physical chips. And the operating system can move chunks of memory around when it feels like it for efficiency or to make room for a memory request, which means the physical address in memory that your variable lives at may change out from under you at some point during the running of your program. You as a developer do not want to have to deal with that. because you are a mortal human, and therefore you are intellectually incapable of writing code that can handle its memory changing out from underneath it. And that's fine, because the operating system and CPU conspire against you to lie to your program and tell it you have one big continuous block of memory starting at address 0 and going up to address whatever. And you can read and write to that, and the operating system will translate that into what the actual places in physical memory are. This is called virtual memory. And without it, you would not be able to write multitasking computers, because you as a human could not write safe code. Even in languages where you have manual memory capacity, not getting your memory management just right is the #1 source of security holes and bugs, which is why A, virtual memory is good, and B, you want to be using languages that take care of memory for you, whether that's garbage collected or something like Rust. Either way, you as a human should not be managing memory yourself in the 99.9% case. Now, if you've actually done operating system work before, you've actually done system level work and dealt with CPU architecture, then you know that I'm actually also lying to you. I am grossly oversimplifying the space. I'm skipping over a ton of details. I'm ignoring CPU caching, hyperthreading, all that stuff, and all the other cool things that an operating system does. That's not relevant for us now. That's a whole other college course, so put that aside for now. But the fundamental point here is that all modern computing requires and is dependent upon the CPU and operating system lying to your program in order to make it think it has exclusive access to the hardware, when in fact it doesn't. That is everything these days. And that's cool. But what if we could, since we already are lying to our programs, what if we could tell different lies to different programs? What could we do then? That is where namespaces come in. Now, everything I've said up till now is true of pretty much any modern operating system. From this point on, we're talking specifically about Linux, not GNU Linux, Linux the kernel here we're talking about. Namespaces are a feature of the Linux kernel that allow you to tell different lies to different processes. You can bundle processes together into a cluster called a namespace, and then tell a different lie to each bundle, to each namespace. Different operating systems often have similar functionality that works differently. Linux is a lot more fine-grained, whereas other operating systems like Solaris or BSD tend to be much more coarse about it. We can talk about that more later. Linux in particular has 6 namespaces that were added kind of piecemeal over time since kind of the mid-2000s. And they're what enables us to lie in creative ways. The simplest is the UTS namespace. The UTS namespace controls the host name of the computer. Very basic. The host name is essentially a single global variable in memory that processes can access to read what the host name of the computer is. And they can also set it using set host name or set domain name system calls. Incidentally, UTS for host name comes from the name Unix timeshare system, because that's what the actual data structure is called, because that's what it was called back in the original Unix in the 70s. So be careful with your naming, it'll be around a very long time. With the UTS namespace, you're able to say, all right, I'm going to create a namespace called web, and I'm going to put process 7 and process 8 in there and change the host name in that namespace to web. I'll make another namespace, put process 9 there, and inside that namespace, change the host name to SQL. So now, if process 1 asks the operating system, hey, what system am I on? It will get the answer, my laptop. If process 8 asks the operating system, hey, what computer am I on? It'll get back the answer, web. Very simple, but this allows you to now have a different global variable for each namespace, essentially, a different lie to each one. Okay, moving up a bit, we have the process namespace. Similar idea, you create a process namespace, A or B or whatever, and then put processes into it. And just like there's an interior and exterior host name, a process can have a namespace local process ID. So in this case, what the operating system sees as process ID 12 sees itself as process ID 2. If it asks the operating system, hey, who am I? It will say, you're process 2. Congratulations. And if process 12, aka 2, asks the operating system, hey, what processes are there on the computer? It will only get told about the ones in its own namespace. It'll get told there's 2 processes, 2 and 3, and that's it. It had process 12 has no idea that this green process over here, process 14, even exists. It can't know that it's there. It doesn't know that process ID 1 exists. It can't see it, it doesn't know it's there. Process ID 1 is not in a namespace, so it can see all 4 processes. If it asks the operating system, it'll get answered, oh, there's process 12, 13, and 14 plus you. What this lets us do is have processes that are hidden from each other with only the slightest bit of overhead, because all we're doing is have a lookup table to change what the lie is for each process. Now, that's great, but one caveat, most communication between processes and most of the API for processes is actually managed through the file system, because Linux does most of its APIs through pseudo files on disk in a directory called proc. Okay, can we split that up? Actually, yes. It's called the mount namespace. Mount namespace is one of the oldest namespaces added, and it's kind of like a super chroot. If you've not used chroot before, essentially you have a big file tree. You can kind of see my hand here. You have a big file tree for your entire system, starting at your /root. But you can, with a chroot, say this particular process, its root directory is this subdirectory. So you can say this process, when it runs, sees root as what everyone else sees as home/me, for example. And that's fine and that's useful, but it is very limiting because you still only have one big tree. You're just shifting the root around. With a mount namespace, you can have a completely new root node in the file system, and then give one namespace, set of processes, one file tree, and a different namespace, a completely different file tree that don't overlap at all. And that file system could be a partition on disk, it could be a network, or, especially important, it can be a file system image on disk. File system image is a virtual compressed file system, another lie, represented as a file on another file system. Think like a .iso file for CD-ROMs, for instance. For those not too young, those are those old round silver disks we used to use in the bad old days to store data on. Same basic idea. That allows you to do, for example, something like this. We put process 4 into mount namespace A, and process 5 into mount namespace B, and we give them different file roots with a different set of files. But then we have another file system that we can mount into both of those, just using normal mount commands. And then those files are accessible to both, but not the files that are not part of its tree. So process 4 has no way of accessing borg.png. It doesn't know the file is there. It can ask all it wants. It will never see that file exists. Just like process 5 has no idea that holiday.mp4 exists, which really is for the best. If you get that reference, it's for the best. It also means that since one of the ways a process can start another process is pointing to a file on disk and saying, hey, operating system, start that. If it can't see the file on disk, it can't point to it, and so it can't say, hey, operating system, start that. So process 4 cannot start any program that's not in its file tree. This gives you an extra layer of security and cordoning off of a process. Next up is the network namespace. This is a little bit tricky. In Linux, you have physical devices. These are a logical representation of a physical piece of hardware, a disk, a keyboard, or more importantly for us, a network jack. And these cannot be namespaced. You cannot namespace a physical device. However, Linux does have virtual devices, which are another lie, this has been around forever, which are a data structure and API logical construct in the operating system in memory that looks like a physical device but isn't, and is in fact a fake hard drive or a fake keyboard or a fake network device, a fake network port. And these can be put into a namespace, and you can also create them in pairs. When we create them in pairs, it lets you move one of them across the namespace boundary and they can still talk to each other. That lets you do something like this. In this case, we have a physical device, ETH0, that's a real physical network jack on the back of the computer, that the operating system can talk to. And then we've created virtual devices, VF0 and VF1, which are bound to each other, and we move VF1 into namespace A. And then we do the same with VF2 and VF3 to namespace B. Now, we can set up forwarding rules in the operating system through various mechanisms so that certain requests, when they come in, get forwarded to VF0, which tunnels through to VF1. And there's a process in namespace A that can only see VF1 and is listening on port 80. It doesn't know that any of these other devices exist. It only knows about VF1. Meanwhile, other requests get forwarded through to namespace B, where there's another process that's listening on VF3's port 80. And VF3 is the only device it knows about. It's the only network port it knows exists. We now have two different processes that are able to listen on port 80 at the same time without bumping into each other. As far as either of them know, they are the only web server running, but we can have 2, 3, 4, 100 of them, and it's just up to the operating system to do forwarding rules. That's kind of cool. Finally, we have the user namespace. The user namespace, well, we said all processes have an ID. Processes also have a user and a group that own them. That's user and group of the system users. And that mainly is useful for affecting access control. Normally, a process can only send messages to another process that is owned by the same user or the same group, depending on various configuration. When we say send messages, the most important one is the terminate command to say, hey, you shut down, but there are others as well. The root user, any process owned by the root user, has superpowers and can send messages to any process regardless of who owns it. It's a special role. The user namespace lets us have a namespace local user that owns a process, independent of a global user that owns that process. Just like the process namespace gave us a local process ID and a global process ID, this gives us a user local user, a namespace local user and a global user. And you can even map that to root. So you can have the root user own a process in a namespace but not out of it, or vice versa. And that lets you do things like this. We have our global non-namespaced space with process 12 in it. Then we have a namespace A and another sub namespace B. Most of these namespaces can in fact be nested. And then we have a user list in the main system, and then a user list local to the namespace A and local to namespace B. So now, in this case, process 38, namespace A, it knows all of these processes exist, but it thinks it's owned by the user Wharf, not by the user Crusher. Process 12 can see it's owned by Crusher in the global namespace, but internally it's owned by Wharf. Most importantly, though, is process 37, which is owned by root inside namespace A, which means that process can send messages to process 38 or 42 or 43 because it's root relative to those other processes. It is not root compared to process 12, and so it cannot send a message to process 12. There's a lot of weird things you can do with this, but the most important is the ability to have a namespace local root user. So you can have processes that have God mode powers over only certain processes, but not others. And finally, we have control groups. The control groups are the only thing here that I'm talking about that is not a lie. Control groups are kind of similar to namespaces, and I'm not sure, they may have been re-implemented as namespaces at some point recently. I'm not sure of that. Doesn't change anything for our purposes. C groups allow you to tweak the scheduler. We mentioned the scheduler before, tries to keep track of which program, which process gets how much time on the CPU and how much memory, but it tries to be fair, but a greedy program can very easily cheat, either deliberately or accidentally, by forking itself multiple times, or just asking for a lot of memory, or just being buggy and slow. There are a lot of things that can go wrong that mean the scheduler can't keep track of things effectively. So control groups let you form a hierarchy, another hierarchy that is separate from the process hierarchy, or the user group hierarchy, or any of the others. And the control group hierarchy has nodes onto which you associate a process and controllers. Those controllers allow you to do things like tracking or auditing or resource capping of processes on the same node or child nodes. There's a dozen or so controllers. These are little programs in the kernel that you can use. For our purposes, we only care about the ones that can control and cap CPU usage and memory usage. And that cap then inherits down the tree. So we can say, put these three processes in on this node in the control group hierarchy, and a child process of that, or a child node of that gets other processes, and say that set of processes collectively do not get more than 1 GB of memory. The operating system will just not give them collectively more than 1 GB. Or they can have no more than 25% of the CPU time. Whatever processes are requesting whatever time, this set of processes gets no more than 25% of the total CPU time. That lets us do things like this, where we can say, all right, let's say process 13, we're going to assign to a C group, and that C group is confined to a single core in our 4-core processor. And nothing else runs on that core, just that one process. And we're going to take all of our Nginx processes and put them in a C group that's assigned to a different core. Every other process on the computer runs on those other 2 cores, but these 2 lower cores are reserved just for these processes. That means that even if something runs amok in the MariaDB process, a slow query or whatever, it may slow down that process. It may chew up all of the CPU time that process gets, but it will never impact Nginx because it's never allowed to run anywhere except that one core. Nginx, meanwhile, it may have however many processes it has, but those will only be in contention with each other on that one core. You can also say they can go on any core, but total only get 25% of time, or 20% of time, or 50% of time. There's a lot of different ways you can configure this, all of which boil down to you as a particular process or set of processes do not get as much resource as you can chew. You get just this amount, and that's it. So that's all nice, well and good, but can you use multiple namespaces? We just talked about a bunch of different things. Can you use them all of them? Can you apply multiple of the same process? Yeah. You can mix and match, in fact, and do some really weird things where you have this group of processes, 3 processes are in PID namespace A, but 2 of them are also in mount namespace B, along with these other 3 processes, and those 3 processes are in a UTS namespace. You could get some really weird stuff out of that. I recommend don't. By far, the most common use of namespaces is to just use all of them at the same time for the same process. They're the same set of processes. So in this example, we have 2 processes, 43 and 37. which are in a user namespace with a local username, a namespace, a PID namespace with a local ID, a mount namespace, so they have a local file system, a vhost, a network namespace, so they have a virtual network port that they can use. They are in a UTS namespace, so they think their name is enterprise. They have 1 GB of memory and only 25% of the CPU that they can use collectively between them, and they can't break out of that. So now we have a set of processes that know only about each other. They have a root user. They have their own file tree. They have their own network configuration. They have their own host name. There's no way for them to get out of that box. And they have a finite amount of resources. Cool. That sounds really, really useful. But when you think about it though, if the processes are that isolated from each other, is that any different than being on their own computer? Not really. They can tell that they're in a C group if they ask the operating system, but they can't change anything about it. They're still sharing a kernel, but that doesn't really affect them. This sounds extremely useful. So we really should come up with a name for this very common pattern of using all the namespaces at once. So we can just use that instead of saying apply all the namespaces at once. And let's just make it convenient, and let's call it a container. I didn't want to break my own microphone, so thanks, Obama. Now, namespaces in practice are really, really fine-grained. For daily usage, you really don't want to be managing those yourself all the time. So what do programmers do? Programmers build abstractions and build coarser APIs on top of these tiny little namespace features that let you do all of them at once in a much nicer way with a better API. That's all these things are. And you can build them in pretty much any language with full system commands. You may have heard of some of them. LXC is the original, Linux, which stands for Linux containers. That's written in C and has bindings for C, Python, Go, Perl, and a bunch of others, so you can extend it. Docker, you've probably heard of. Docker started as a layer on top of LXC and then forked off and re-implemented its underlying layer with something called LXD, I believe it is, or something like that. Rocket is another one that forked off of Docker when they decided that the Docker company wasn't doing things they liked. Yay, open source. You may not have heard of some of these others. Vaga is one written in Rust. Bocker is one I found that's written in Bash. You can do a container engine implementation in just Bash script. I'm not going to suggest you use it in production, but you can do it. It's worth reading just to see how easy it can be. You can do this in basically any language that has full support for POSIX system commands, which is almost everything except PHP and possibly JavaScript. Another concept you may have heard of is orchestration. Orchestration is the process of keeping track of many different containers and their settings. Because in practice, most of the time, turns out you don't actually want a single container. You want to have multiple containers that talk to each other as though they were a cluster of computers on a network. So the process of setting up several of those at the same time is called orchestration. Someone should mute. The big name in the space is called Kubernetes, but it is by no means the only tool for doing so. It's just the one that gets the most press these days. But that's another important factor, is keeping track of all of these different containers in yet another abstraction, yet another coarser API, yet another lie on top of the pile of lies we've already had getting to this point. Very often, containers are implemented with a read-only file system. Don't have to be, but usually are. Why? Several reasons. For one, if the file system is read-only, you can launch multiple containers with the same file system tree image, and the operating system only has to load it into memory once because it can detect, hey, this is the same thing. I'm not going to waste memory by copying this 300 megabytes or more file system image multiple times. I'm just going to use it once. It also means you can avoid write collisions. If you have multiple sets of processes all reading and writing to the same pseudo partition, the same file tree, well, you have to make sure that they don't step on each other's toes. If they can't write, there's no toes to step on. So it makes things less likely to break, makes it easier to maintain, easier to coordinate. Also, the overhead of this is all pretty easy. Namespaces are very lightweight. They're really just a translation table so that when you call the operating system, your request goes to a translation table before doing what it is you want it to do. The overhead for that is tiny. It's just a little lookup table of lies. So this means you can run 50 copies of the same container, 50 copies of the same process with a given file system image with very little overhead, because the operating system can recognize 98% of that is duplicate, so don't duplicate it. Linux is kind of smart these days. Now, one of the promises of containers is that, oh, you build a container, you can run it anywhere. That is a complete and total lie. That's marketing mumbo jumbo. For one thing, anyone who's ever tried to use Docker in production knows that's not actually true. For another, it's talking about the wrong piece. Containers, if you have a container image that's a file system with specific instructions for what the namespaces should be and how they're configured, that's going to be specific to any given runtime. An LXC container is not going to run on Docker. A Docker container is not going to run on Vaga. A Vaga container is not going to run on LXC. All of that is still very specific to that particular container runtime. It's like essentially different file format. It's like, a PNG versus a JPEG, same kind of difference. But that's not the important part. The important part is not that you can plug a container into any system. The important part is what's inside the container. Because with the container, you can control explicitly what all of the dependencies of your program are. Your program has hundreds of implicit dependencies you don't think about. A simple hello world PHP script, for example, has your PHP script, then the specific PHP version you have, the specific libraries, shared libraries that are plugged into your PHP engine, your specific version of Nginx, your specific version of PHP FPM, the specific compiler settings those were compiled with, the specific operating system, specific compiler settings your operating system was compiled with. There are billions of possible combinations of software here with slightly different versions of each of those, every single one of which has a completely different set of bugs. And you don't want to debug billions of different possible sets of bugs. You want to debug one set of possible bugs. But if a process starts another, it loads its dependency by just pointing to disk and saying, hey, operating system, start that. If you provide it with the complete disk image of every dependency it might talk to, then you can control the exact version of every one of those dependencies. That's huge. That means you don't need to worry about this. Is this working on node 11.0.3, but not 11.0.4? Not to deal with that. No, you build into your container 11.0.3, and that's the end of it. That's what gets used in every case. You can ship exact copies of every single file and every single process that your application requires. Essentially, it's like a static compiler for your entire operating system, for your entire computer. That's kind of cool. It's also one of the reasons why Go is a very popular language for heavily containered applications, because Go is designed to compile all of its dependencies into a single binary, which makes the container image you then need much, much smaller. Certainly other languages work great with containers, but that aspect of Go is very tailored for, I think mostly by accident, very tailored for a container type environment. Now to see this in action, I want to talk about two different container systems. I'm going to talk about what we do at Platform.sh with containers and what Docker does and how those differ, not in a better or worse kind of way, but just different tools for different use cases. First, let's talk about Platform.sh. I said we're a container-based cloud hosting environment. We built our own container system on LXC. We don't use Docker. We actually started building our system before Docker was even usable. And most of our code is Python that is coordinating an LXC driver under the hood. We use a nested squashfs file system for our disk images. I'll talk more about that in a moment. Squashfs is a highly compressed, fast to decompress, read-only file system image. So you can take a big chunk of files, squeeze them into a single file system that is very small, but decompresses quickly, and then is read-only, guaranteed you cannot modify it. And then our orchestration system is built in. We don't have a separate concept of single container. Everything is multi-container in our case. So orchestration is not a separate concept from our containers themselves. What we do is you have your code in Git, and you push that code to Git repository on Platform.sh, or integrate with GitHub or Bitbucket or whoever, and that can push to Platform. Git is cool like that. We then check out your source code into a temporary space and run a shell script on it. That shell script is whatever build script you want, you provide that. That can be basics like installing Composer or NPM or bundler dependencies. You can compile Sass or less. You can compile Go or Java or Elixir. You can run JavaScript compression tools, whatever you need to turn your source code into your actual runnable artifact. Even in scripting languages these days, there's always a build step to turn thing in Git into thing you actually run. The output of that is a squashfs file system. We take the result of whatever that is and make a squashfs file system out of it. Then we create a new container with a base image based on what you select. You have config files in your Git repository that say, here's my build script, and I then want it to run on Ruby 2.6, or I want it to run on PHP 7.4, or I want it to run on Go 1.14, and so forth. And those are a base OS image that we provide that's based on Debian. We then just do a normal mount command, normal file system mount command, to take the built application image and just mount that into a standard directory. Into that, we can then mount a temporary RAM disk for generated configuration files for things like Nginx, and potentially network-mounted file partitions that are writable that, again, you can control via your config files. So we have, when you build your environment, this multi-part container that's just normal Unix mount commands to assemble it, with the instructions on this is how much CPU it gets, this is how much memory it gets, this is the process that should start, and so on. Inside that container then, you have a complete running operating system, but it's very lightweight. This is a PS command from inside one of our application containers. This one is running PHP. And we use this is runit is our process manager. So that's process ID 1 inside this namespace. And then run svsh, the fourth line here, is runit starting up SSH. Runit has a couple of extra processes it uses for control purposes. But that first block there is just, that's the SSH daemon running, and me logged into it running ps AXF. Then there's Nginx running, and there's PHP FPM running, and that's it. The physical box, actually the VM that this is running on, has hundreds or thousands of these containers. Inside the container, it feels like a complete system because we're providing a complete operating system, a complete file system with a complete init process. Also note that this is, again, very efficient because that base image is shared by every container. It's exactly the same bits for every PHP 7.2 container. This is a bit of an old slide. Every PHP 7.2 container on the system. So that disk space is used once. That memory space is used once. As I said, though, for us, cluster is the unit of deployment, not individual container. So when you push, you also have a config file that says, my application requires MariaDB, and it requires Redis, and it requires Elasticsearch, and it requires RabbitMQ, or whatever. And then we can build containers for those too that work exactly the same way, except there's no custom application image that gets used. Everything else is still the same. We have a base image that we provide for MariaDB, and we mount a writable file system into that. And we have one for Redis that doesn't need a file system because it's all in memory. Cool. And then we can turn on all of those containers at the same time, and you now have a complete cluster that is your application based on your definition. When you want to update the application, we can just temporarily close network requests to your cluster. Actually, we first build a new squashfs image for your application, the yellow one on the left. Then turn off network requests, run the mount commands to unmount the file system, unmount the writable file system, unmount your old application, mount your new application, and remount the file system. And then we turn everything back on. And that can happen in a matter of seconds. This allows you to upgrade a complete file system image very, very quickly. Give or take some scripts that you can run yourself. Those can take seconds to minutes, depending on what it is you're trying to do. But this allows us to use containers to give you what feels like 3 completely independent computers that logically are 3 independent computers that may or may not be running on the same virtual machine or may or may not be running on the same hardware. We don't know, we don't care. Neither do you. And then guarantee easy updates, guarantee a stable deployment because the base image didn't change if it didn't have to. It also means that we can easily clone an environment by taking that file mount and creating a logical copy of it, a copy on write copy of that, and then take the same instructions and spin up a completely new test environment on another branch in Git that uses the exact same underlying PHP image, MariaDB image, and Redis image, and plug the exact same application image that you built into it, and then plug our copied file system into it. And now in a push of a button, 2 minutes later or so, you have a complete copy of your entire production site, code and data that you can play with. Containers make that possible because we're able to lie to all of these processes. We can lie to PHP, we can lie to Nginx, we can lie to Redis, and duplicate these environments as much as we want. Now let's compare that to what Docker does. Docker is built on a completely different model for a different use case. In Docker's case, there's a layered file system. Docker does not use an init process at all. In fact, it's optimized to put only a single process per container. If you ever ask why Docker tells you don't try to run more than one process in a container, if you're doing PHP, you put your Nginx and your FPM in separate containers, this is why. There's no init process, which is fine, but does limit what you can do. The file system then does something kind of orthogonal to what Platform does. In this case, you have I'm not sure if it uses UnionFS under the hood or not, but you have a baseline image that's, say, just a bare bones Debian install. On top of which you layer, kind of like a transparency or a layer in Photoshop, another file system image that is MySQL, and then another file system image that is your home directory. That has a number of advantages because it means if you have a whole lot of systems running slightly different top layers, they can all share that same bottom layer. You don't need to build a Debian with MySQL, a Debian with Redis, a Debian with Solr. You can just have the same Debian and then layer on top 3 different times those other applications. On the downside, it makes reading and writing more complicated and harder and therefore slower. Because if you're looking for, say, the etc hosts file, then what the operating system has to do behind the scenes, you don't actually see it, is look, okay, etc host, is that in the first layer? Nope. Okay, check the second layer. Nope, check the third layer. Okay, oh, find it, and then pass that back. So this gets really slow when you have more layers. That's why good recommendation for Docker, when you're building a Docker image, is to only have is to have as few run commands as possible. Every run command adds another layer of, another Photoshop layer here to the file system image. So different use case, different trade-off. Docker works really, really well when you have a lot of containers with slight variation between them. or when you're running a single one-off process. It's fantastic for, I want to run this command line tool or this temporary process locally. Docker is great for that. If you want to do very controlled, high level, this is what a PHP 7.2 container looks like. This is what a Elasticsearch 7 image looks like. This is what a Go 114 image looks like, and so on. Then the system we have at Platform works way better for that. Docker is fine for local use. I much prefer our setup for doing widespread hosting. There are other options too. If you've heard of Ubuntu Snaps or Red Hat's Flatpak, those are container-based systems that work differently than either one of these for doing local applications. So you can download Slack or Discord or some other application as a completely contained little file system image for running a local application. Snaps and Flatpak, I don't know enough details about how they're implemented to talk about them in detail, but those are container systems optimized for that use case, which is a totally different use case than either of the ones we're talking about here. So at the end of the day, enjoy your lies. All software is built on lies. As developers, our job is to lie to the computer. We have an enormous number of tools for lying to the computer. And containers are a new way for us to lie to the computer in order to get it to do what we want. Embrace the lie. The entirety of cloud computing is a lie. The entire industry is built on lies. And I'm actually the good kind of lie, not just marketing lies. Everything we do as developers is a lie, except for the cake. Thank you very much.